So at this point you've completed this worksheet here, and if you haven't completed this, then you should print it out from the materials, right, and then complete what we have here. Okay, so you've answered this. So let's just talk a little bit about what this tells us. Okay, sorry, because really we're doing continuity, right, for ourselves, and we're thinking about what continuity means. And we've already used this term, right, talking about continuity, and we've already talked about how like this function is really not continuous. And I said, where is there something, where's something happening? And for this one, we had their asymptote at x equals 2 for ourselves. Okay, and so that's one of the stipulations for continuity, is that you have to basically, you can't have any points where there's any domain restrictions, any points where the graph is discontinuous here. Right? So for this one, right, this is discontinuous at x equals 2. It's, if I said where is it continuous, it's continuous on the interval negative, right? Well, actually, technically for this one, if the question was where is this function continuous, right? Well, we'll get into that question later. Sorry, that's a little bit hard to get into. Okay, so if the question is discontinuous, it's at x equals 2. Okay, because basically to be continuous, you have to have a couple stipulations, right? So to be continuous, right, then a function must satisfy the given conditions for all points in the domain. Okay, and this is the key thing, for all points in the domain of the function. Okay? Right. So first thing is that f of c must exist. Alright, maybe I should change this to all x values. C. F of c must exist. Okay, and the second one is that the limit of f of x must exist at all points. And the third one is that, and this is really the only one you really need, you could just sum it up with this, is that the limit equals the value of the function for all values of x, all c in the domain we have here. So if we're looking at this, right, if you have this point right here, right, the limit equals the actual value, right, so the function is continuous at x equals -1. The function is continuous at 0 because the limit equals the actual value. If I were to ask the question here, is this function continuous? The answer would still be yes for it. Even though there's a point of discontinuity right here, for all values of x within the domain of the function, right, this function would probably in all likelihood be this, and I'm just going to assume that it's this right here. Okay? Minus there, sorry. So, for all values of x, right, within the domain, the limit equals the actual value. So it's kind of weird. This is an example, right? If you have this is an example where the limit exists, this is an example where there's a point of discontinuity, but the function itself, if you were asked that general question, is the function continuous? The answer would be yes. For all values of x within the domain of this function, it is continuous there. Okay? Now, let's take a look at this discontinuity we have at x equals 2. Right? Even though the function is discontinuous, there is a discontinuity, right, at x equals 2. And if we look at that type, we can see that the directional limits are going up and down to infinity. Okay, so this is going to be called, so this is classified as an infinite discontinuity. Infinite discontinuity. Okay? Because it's going up and down to infinity. Okay? And it's also, right, classified as a non-removable, right? Because, well, I'll get more into why it's non-removable, but I'll get to that in a second. Okay? So if we look at this, right, at -1, right, we can see that the value, right, it kind of hits the stipulation step number 2 here, that the value actually exists, but since the limit doesn't exist, right, then, okay, this one's not going to be continuous there. The answer to this question here is no. for ourselves. So these A, B, and C's were basically the step 1, 2, and 3 of determining if a function is continuous, right? Since it's not at -1, right, then the function would not be has a discontinuity. There's a discontinuity at x equals -1, okay, for ourselves. And excuse me. And if we look at that type, we can see what the directional limits do. The directional limits here approach finite values. Okay? Since they're approaching finite values, this would not be an infinite discontinuity. It's not approaching infinity. Okay? What we have instead is that the function, which was up here, and then it jumps down to this value over here. So we see a jump in the values of the function, and that's why this is going to be called a jump discontinuity. Okay? For ourselves. This is also going to be classified as non-removable. All right, and I'll show you, and it might help that I show you what a removable looks like to understand this idea of non-removable. This right here is a removable discontinuity at x equals 0. So there's discontinuity at x equals 0, and it's non-removable. I'm sorry, it's removable. Why is it removable? Because you removed a point from the graph. Right? If you look at it, this point was taken out for ourselves. Right? You basically, in this case, the limit exists, but there's just an open circle. Okay, so anytime it's a removable, you can just basically say this is an open circle on the graph. Okay, that means it's removable. Discontinuity. Okay. If it's a removable discontinuity, the way to prove that is that the limit exists. Right. So if the limit as x approaches c exists, but is not equal to f of c, it's a removable discontinuity. And that's the big takeaway. I would highlight that if you have a highlighter. I forgot to bring my highlighter down right as I did this, but right, so I'd add that if I were in your shoes. Okay, that's the key. Okay, I'm going to ask you to prove the types of discontinuity. So if I'm going to ask you to prove it's a removable discontinuity, you would first, tell me it's a discontinuity because it's domain restriction, or that you would basically say f of 0 doesn't exist, but the limit of as x approaches 0 it exists, and so that's why it's going to have. That's why it's going to be removable. If I was going to ask you to prove that's infinite discontinuity, you would just prove that one of the directional limits approaches infinity. It doesn't matter which one. You have one side and it's an infinite discontinuity. If you're going to prove that it's a jump discontinuity, you would just prove that the two directional limits are approaching finite values. That's really what you have to do. Okay? So let's take a look at this. Okay? So we're looking at example 4. Hopefully you did these already. Okay, right. This is the find the values for which the function is continuous. Right, it is continuous for these values. But if I asked you, is the function continuous? Right, if the question was, is the function continuous? That was the question instead. The answer would be yes. Yes, the function is continuous because for every point within the domain of the function, the limit equals the actual value. You have to think about that part when you ask that question, is the function continuous? You have to go back to that strict, that part about the definition that we did when we talked about continuity, right? That a function must satisfy the given conditions for all x values in its domain. Right? If the points are not in the domain, then we don't worry about that when we're asked this question, is it continuous? If the question is find the discontinuities, or find the values for which the function is continuous, right? You can't say that this function is continuous for all reals. It's not continuous for all reals. But if you're asked this question, is the function continuous? The strict answer would be yes. Right? Is this function continuous? If I asked you that, is this function continuous? Again, the answer would be yes for all domain values for that function. Right? Then the limit equals the actual value. Right? Now, does it have a discontinuity? Yes, it has a discontinuity at 0. Right? But that 0 is not a member of the domain, so that's why the function, if you're asked that question, is the function continuous, that's why the answer would be yes. Okay? This right here would be a removable discontinuity because our point has been removed. Right? This right here, as we just talked about, that would be a non-removable discontinuity. Right? This one right here, take a look. All right. Now, my guess is you probably put parentheses around this, right? But it's actually brackets. So there's a key special point for endpoints of an interval. Okay, for if you have endpoints of an interval, okay, right? All you need is the directional limit to equal the actual value. Okay. Again, C is this X value that you're picking within the interval. Okay? So that's why this one has a bracket right here, because this is an endpoint of an interval, right? So you would have that there. Okay? This one here, technically, right? If we wanted to go strictly speaking, right? And if you're going to be an engineer, right? You would look at this. Technically, that has a bracket there. Okay? That's the endpoint of an interval that we'd have. This interval word for that function was a piecewise function. Right? I usually put parentheses there because that doesn't make sense to me. Right? That if you look at this, right? You would say, shouldn't I put those two together because it's continuous at -1, it's discontinuous. It's kind of a little weirdness to it that they actually wouldn't go together. It's because of the type of question you're asking. The question is asking, where is the function continuous? On this interval, right, it's continuous at the endpoints of it because the directional limit equals the actual value. Notice that this would be an open parenthesis because the directional limit does not equal the actual value. Right? Okay? Same thing here. Directional limit doesn't equal the actual value. Here, directional limit does, so I should have brackets there. Okay. If you put parentheses there, I'd be okay with that, right? These ones have to be hard brackets because those are truly the endpoints. But some people, and if you think about it, for some later calculus applications, putting a hard bracket there doesn't really make sense, right? So it does make more sense for the parenthesis. Excuse me. So if we look at this one, we said, is this function continuous? If for this one it's just is the function continuous? Your answer would be no. For the x value of -1, the actual value does not equal the limit. So if you're doing continuity, you would be thinking to yourself for every point. By the way, for what it's worth, if I were to go back to this one and put an extra point right here, okay, if I did that now, and the question was, is this function continuous? The answer would be no. It's because at the value of 0, the actual value does not equal the limit. So by putting that point in there, right, I now don't have a domain restriction. I filled in that domain restriction with basically a piecewise function for myself. Okay? So those are some of the nitty-gritties of continuity there, right, to help you to understand what it's going to be.